Here we apply conservation of energy to an incompressible fluid flowing in a steady state through this pipe here. And we're going to derive what's called the Bernoulli equation. This pipe graphed here shows the horizontal direction x and the vertical direction z. And we've got a side view of it, but you should be imagining a sort of a three-dimensional pipe like so. Instead of being round, let's say that it's sort of a rectangular or square in cross section. So we've got fluid filling the whole pipe with the rate of flow entering the pipe at the left, matching the rate of flow exiting the pipe at the right, since we're in a steady state. You can picture this cross-sectional area, this rectangular area here at what we'll call gate 1, and then this square, smaller cross-sectional area here at gate 2. And the blue fluid filling the space between gates 1 and 2, that's what we're going to call our system, with some other fluid, this purple fluid behind it, pushing the blue fluid forward, and then this fluid in front of it pushing backwards on the blue fluid. So the blue portion of the fluid is our system, and if it's all moving through here in steady state flow, then some short time later, delta t, the fluid that was between gates 1 and 2 will now have moved. Some of it will have passed through gate 2 up here, and then some new fluid will have come in behind it, passing through gate 1 there. So between these two moments in time, work will have been done on our system here. Work from this force due to the pressure from the fluid behind it pushing it forward this distance, delta x1, and also work done by the force from the pressure of the fluid in front of it pushing backwards on it as this portion of the system moved forward a distance, delta x2. So the net work done on the system, on the blue section of our fluid, by those pressure forces will be this sum. The force from pressure at gate 1 times the displacement, delta x1. That'll be positive work since that force and the displacement are in the same direction. And then also here a negative work done by this pressure force up there, since this pressure force and that displacement are 180 degrees apart. So negative work being done there. Let's express those two pressure forces as the pressure at gate 1 times the cross-sectional area of gate 1. And then likewise, the pressure force at gate 2 will be the pressure at gate 2 times the cross-sectional area of gate 2. And with these two expressions, I'm going to note that A1 delta x1 and A2 delta x2, those are the volumes of fluid that have passed through gate 1 and passed through gate 2. And since our fluid is incompressible, the volume that passed through gate 1 must be equal to the volume that passed through gate 2. So these two expressions are equal. We're just going to call these both delta V, and then we can write that the net work done on the system will be equal to pressure 1 minus pressure 2 times that volume, delta V, of fluid that passed through each of those gates. So delta V being given by this, that's the volume of fluid that passed through each gate. Okay, so we've got this expression here when you see that work will have been done on our system if there's a difference in pressure between the fluid behind our system and the fluid in front of the system. If these two pressures are different, then as our system moves, there's going to be work done on that system. That'll count as a non-conservative work. Let's then look at the change in mechanical energy of our system. In this picture, I'm showing in light blue here the fluid element that, is no longer part of our system. So the mechanical energy carried by this fluid element is no longer part of our system. But on the other hand, over here, this fluid has now become part of the system, or rather our system has moved to include this area here. So the mechanical energy carried by this fluid is now part of the system. So the system lost the mechanical energy carried by this fluid element, but the system gained the mechanical energy carried by this fluid element. So we can write that the mechanical energy of this fluid element here that passed through gate 1 is going to be its kinetic energy plus its gravitational potential energy. Let's say the mass of this fluid is little m here. So here's its kinetic energy, where V1 will be the speed of the fluid passing through gate 1, and Z1 will be the height of the middle, let's say, or the sort of center of mass, height of the center of mass of this body of fluid here at gate 1. So then the sum of these two terms we can re-express if I replace the mass of that fluid element with the density of that fluid element times the volume of that fluid element. And since the density of fluid is the same in both locations, and these delta V's are the same as we discussed, the masses of these two fluid elements must be the same. So in this expression, I'm going to factor out the delta V to get a couple of terms that we refer to as energy densities. 1/2 times the fluid density times the speed at gate 1 squared, plus the fluid density times little g times the height of the center of mass of the fluid at gate 1, and factor out of both of those the volume of those fluid elements that have passed through each gate. So if this is our expression for the energy, the mechanical energy carried by this fluid element that was lost from the system, then we can get an expression for what we'll call E2, the mechanical energy gained by the system, the mechanical energy carried by this fluid element, just by replacing these ones here with twos. And so we'll now write the change in the mechanical energy of the system can be found by taking minus this expression. This is the mechanical energy lost from the system, so minus E1. So that's this term here. And add to that the mechanical energy gained by the system, that's this, which is the same expression with twos instead of ones. So that is this term here. So here's the mechanical energy lost. Here's the mechanical energy gained. So that sum is the change in mechanical energy of the system, and that should be equal to the work done by non-conservative forces, and the non-conservative force doing work is the force due to pressure. So the work due to pressure, and from above we have this expression here. And now looking at our conservation of energy equation, we see that these delta V's are the same and can cancel out. And now I would like to collect terms. Let's gather all of the gate 1 terms over here on the right-hand side of the equation. So that will look like the pressure at gate 1 plus the kinetic energy density at gate 1 plus the gravitational potential energy density at gate 1. And then the remaining terms, the gate 2 terms, let's collect those over on the right-hand side to write that the pressure at gate 2 plus the kinetic energy density at gate 2 plus the gravitational potential energy density at gate 2. And so our conservation of energy equation has been rearranged to show that the sum of pressure plus kinetic energy density plus gravitational potential energy density at one moment is equal to that same sum at the other moment. And since those two moments aren't special, this should apply for any two moments anywhere along some streamline. So if we picture just some streamline through our fluid, we can compare that sum of three terms at any moments along that streamline. And our calculation shows that the value of those three terms here should be equal to the value here and here and here and here. In other words, this quantity, the sum of the pressure at some location plus the kinetic energy density at that same location, which is based on the speed of the fluid at that location, plus the gravitational potential energy density at that location, which is based on the vertical position of the center of mass of the fluid at that location. The sum of these three terms, which we'll call just some constant C, must be the same at all points along a streamline. And this is what's known as the Bernoulli equation. It says that as we move along a streamline, we can say reduce the pressure, but then one of these would have to go up to compensate because their sum has to remain the same. Or we could increase in pressure, but then one of these would have to go down, or any other such possible combination. The concept here is that a moving fluid element exchanges pressure for speed for height. If you gain or lose height, you got to gain or lose speed or pressure to compensate for that in order to conserve energy. Let's take note of the units involved here. Pressure, we can express in newtons per square meter, since it's force per unit area. These two terms are what we call energy densities, which just look like energy, like 1/2 mv squared would be joules of energy, but this is mass over volume, so that makes this joules per cubic meter, energy over volume. Likewise here, mgz would be joules of energy, but over volume is joules per cubic meter. These are energy densities. So apparently, if we can add these things together, they must have the same dimensions. So a newton per square meter is the same, or has the same dimensions, as joules per cubic meters. Pressure has the same dimensions as energy density, energy per unit volume. But that's not to mean that they are the same thing. They're not, they just have the same dimensions, so it's possible to add them. And with this Bernoulli equation, we see how we can exchange pressure for speed for height.